Alright, here's the circuit I was trying to show you. And, the circuit we were looking at on the bench is represented by this little box here. But all the rest of this stuff is what would be required to actually turn this into the project I had in mind. You can see these are like the channels, like channel A, channel B, and channel C that input in this. Channel A and B can act as triggers to start and stop that timer module, and channel C can actually act like a counter, so you can actually use that for the timer. If you want to set it in count mode, you can have it count things really fast or really slow, or however long you want to take. It's a 32-bit counter slash timer, so that's like 4 billion counts it can do before it's reset. But at any rate, this right here is again one of the channels. Here's the other two channels, so you'd have this circuit times 3 basically, and these would be on separate cards. That's why I have this blue box around them. And this is the trigger unit, which I had to actually verify in a circuit simulator to make sure it was going to work, involve some flip-flops, and this is allows channel A signal to go high and stay high, and then to start the timer or start the count, and then channel B to go high and stay high to stop it. So that's what's special about this particular timer. Now this down here is a toggle based flip-flop. This is just a set reset. That's how I'm using it. But here I set this up as a toggle flip-flop, so basically you can have channel A come in and start it, and then with a single pulse, and then stop it with a single pulse. Or you can have channel A start it and channel B stop it, or channel B start it and stop it, or channel B start it and channel A can always start it and stop it, but channel B can be set to start only or stop only, or both. So they just both toggle this flip-flop, so it basically starts the counter and stops the counter. Now right here, these are these little buffer chips I use that are tri-state output gates. And again, all these chips, the reason I'm using them is just because I have them in stock. I mean, like 20 years ago, I bought a big IC kit from Jamico, which I've hardly ever touched. So, but at any rate, this allows you to select either, using this as its as a control, for its count enable line, or this one as its control, or you can just feed channel A as a raw signal into it. So if you wanted to like time how long it took channel A's pulse to go from low to high, and then eventually back down to low again, you can do that through this channel. And here, this allows the Arduino to actually feed a signal to it, if you want to have independent control of it for some reason. And these are all going on this bus line, which goes over to these various shift registers, and I'm using these shift registers, which again, this timer, as I explained before, has a 32-bit shift register on it. But down here I got some various other shift registers that I'm using to basically control this thing, so I don't use up all the pins on an Arduino Uno, because that's what I was wanting to see, if I could do this with an Uno only. So but yeah, you do that with shift registers, and these are regular shift registers, and what's cool is that you can use the SPI bus to control them, as long as you take certain precautions. So one of the precautions you got to take, you can kind of see here, this little gate here, is actually one of those tri-state buffers from up above there, and that is handling the output of one of these shift registers. So if you want to shift data back in to the MISO line, master input line, well, you've got to use a tri-state buffer, because these are regular shift registers, and as a result, when you're either shifting them or not doing anything with them, they're going to not tri-state. I mean, they're gonna, either be high or low. Well, that bogged down the rest of your SPI bus, so it couldn't communicate, and maybe even fry some chips, creating some short circuits potentially. So the fact of the matter is, especially since these are LS chips, they can be fried. So they don't have any kind of real current limiting. I mean, you can pull a couple hundred milliamps through a single chip on an LS circuit just from it getting short-circuited. So on one of its outputs, so you got to watch that. The HCTs I don't think are as vulnerable to that. I understand that they're current limited, but I'm not totally sure to what extent that's true. But I don't think they're as vulnerable to short circuits as these things are. So these old TTL type chips were pretty vulnerable to that sort of thing. But at any rate, this is the start of the shift register, and I've got a 164 here I'm using, and that's a 8-bit output shift register. So whereas the ones I used on the counter were 166s, so the timer module you saw in the last part of the video, those are 166 shift registers, so they're input, 8-bit input shift registers. These are 8-bit output. So at any rate, I feed them into this octal transparent latch, which honestly, this chip looks like it'll be a motherfucker if you want to go actually route it, because of how they laid the thing out. It just really sucks. But there's a better latch that you have, but I just don't have a lot of those in stock. And by all means, I really wish I had some of those, like 593s, LS 593s or something like that. 595s is what they were. Those were really cool little shift registers because they actually had a transparent latch built into them. So, so anyway, that'd be cool. Hopefully I can pick some of those up, but I only have one of those in stock. So, up here I used an LS195, which is a 4-bit shift register, which is gives you simultaneous outputs and inputs. So, so basically you can shift data into it, for example, and it'll show up as you shift it. It'll show up on these lines right here, and your transparent latch can then be cycled. You just output latch enable it. You strobe that strobe its latch so it latches in the data, and then you can actually do a shift load on it to read in the data over here, and then have it shift. When you're ready, you continue to shift the data on through using the SPI bus, and eventually you'll get the data from these pins shift out, into your MISO line, which goes through this chip here. So again, this shift register feeds daisy chains right into this. This daisy chains into this daisy chains into this, which is another 195, and another 4-bit output latch. 74 LS75, which I could have used one of these motherfuckers to replace these two chips, but again, these things are so squirrel. That's one of the big reasons I don't think I'm looking forward to even thinking about doing this circuit, because these are going to be a pain in the ass to route, given how they're, how these guys pinned this out. I don't know what they pinned it out for, but it really sucks, because the inputs don't go from one side of the chip to the other side of the chip. They go from one pin, here's your input, and then here's your output. It's almost like a 7404 or something like that. Even a 7404 would be nice sometimes if if you had your input on the left and the output on the right hand side of the chip. Sometimes that would come in really handy. And these, holy shit, it would be just a nightmare trying to route these the way I want to use them. But again, they do make shift registers that actually are transparent latches that are actually arranged the way I want them, but I don't have like 2 of them in stock, so I don't want to, and I forgot what the number is. But at any rate, yeah, it goes through this big shift register chain. Now these inputs on this shift register I'm not using, but there may be a use. I could put some toggle switches on it or something, if I wanted to read some external switches or some shit, but I didn't really have a plan for them, so I just let them open for right now. But in total, this is 8 bits here and 8 bits here, so it's like a 16-bit shift register, and with latched outputs. But again, driven by the SPI bus. Now the SPI bus, how I do that is I actually, believe it or not, use another shift register to program which thing I want the SPI bus to apply to. So this is yet another shift register that comes off the SPI bus, and it has its own independent enable pin, which is this right here. Unfortunately, on KiCad you can't highlight things. They don't really. That's one of the things that sucks about KiCad. These idiots decided to do it in a totally retarded way. But at any rate, I can't highlight these lines like I'd like to. But this is one of the control lines that comes from the Arduino up here. But that is dedicated to this activating this shift register. But once the shift register is activated, basically these things will come and actually that may not be the line, that's the line to this chip over here, but anyway, it does have its own lines somewhere. I had to use all these stupid labels because this is getting too complicated. But yeah, this is another 8-bit serial bus, which you can kind of see one over here, because I was going to put another 8-bit section, but it turned out I didn't use it. But it's pretty much the same thing we were using over here. So, but the point is that you can select, that basically this will pay attention to the serial bus, and it also does kind of turn some of the other things off, like this little RAM chip. This is like a 64K kilobyte RAM chip, serial RAM chip, but I actually have it individually controlled, so I can make it ignore the serial bus when I'm trying to load this thing. All the rest of this stuff doesn't have a problem with it, but because again, the MOSI, the output actually goes to every chip, so it and so does the clock line. So it actually tries to clock, all these shift registers, but most of them it doesn't matter. What matters is that the latch, is enabled, right? So that's all you really care about. It doesn't matter if data is shifting through these things or not. What matters is, are the latches enabled? On the other hand, on the timer module, though, that we showed in the other video, I did actually have it disable for it, just so that shift register glitches don't get in there, since that's kind of a high frequency thing. So I have the ability to turn it off using this set of control registers. I think, in fact, I don't know, it may have actually been disabled differently. But the fact of the matter is that this kind of works the same way, but you can use the SPI bus to kind of stream 8 bits of flags in here. So basically you can enable and disable these various SPI bus slave select lines. So so that allows you to select which thing is actually being used versus not used at the time, and you'd have to kind of cycle it through, because they are the save select lines. So every time you wanted to change it, you'd have to cycle it through this. At any rate, that whole system may change a little bit if I ever did this, but again, I just wanted to put the preliminary design out here to look at the plausibility, because I didn't even know if I'd have enough pins on this thing to actually do this or not. I was really in doubt. But again, the use of all these shift registers, I managed to get around a lot of those concerns. But again, I still haven't even verified, that all these wires are routed to the right places yet, or anything. But all I care about is that it's explained. And here, these are little, input modules, which involve an attenuator, through a potentiometer, and then a couple of Schottky diodes for protection of your digital logic. You can kind of see that we got these channel A, B, and C lines, which feed directly from those these output modules over here, so the Arduino can actually deal with those directly if you want to. Because there's some things that are better done in Arduino mode, like for example, you've got the 3 analog to digital converters, which these 3 inputs go to. And that allows you to actually do much more sophisticated measuring and things like curve plotting. If you're trying to measure the charge rate of a capacitor and you want to data log it, you can do that through this, but it's of course a lot slower, limited about 20 kilohertz or so events. But the point is that if you wanted to do that, you could. There's a lot of different things you could do this, that I'd probably deal with when I get to code. But the fact of the matter is, just dealing with the Arduino alone and a few of these components, I can basically achieve the same thing just a lot slower, but I can get rid of almost all the circuitry if I want, including the timer module itself, and just use the Arduino, and again, some of these things, and, like the, displays and so forth, and then these are all modules, as you can see, these are like temperature modules, and, and some weight sensor modules I thought I'd throw in, for the hell of it, because maybe you can make weight trigger it, two different weight sensors could trigger the thing too. You kind of try to measure, okay, when the bottle of water is filling up, when it weighs 1 pound, start the count. When it weighs 5 pounds, stop the count. How long did it take it to fill up? That kind of thing. I mean, who knows what you're measuring too? I mean, it could be, rates of rainfall, or, who knows. The point is that this is, meant to be a really versatile circuit. But again, I can still do most of this stuff with just an Arduino alone and some simple, external circuitry, including this down. Where is it? Not that. Yeah, I moved everything around from earlier. It's not this. Oh, it's this. Yeah, it's not its own separate little module with this SRAM chip, it's good for if you want a data log. Well, you can, this is pretty fast because it's on the SPI bus, so, yeah, you can, store and retrieve data to an SRAM chip really fast. And again, you got a graphic display, a 12864 type display over here, that you could maybe drive directly, again, through the SPI bus, more likely than not. But I still, I have those little digital oscilloscope modules, that have a nice color graphic display on them, that you can buy from Amazon for like $20, with their little 150 kilohertz oscilloscopes or something like that, that are Arduino based. At any rate, I got a couple of those. I was thinking about if it, because those are based actually on they're not Arduino based, they're actually based on an ST processor. So I was thinking, depending on how much room and memory that code takes, I could rewrite some of the code and add some functions so I could do a data logger display on one of those little oscilloscopes. So that's why I have what the hell did I do with it? Let's see. I don't know. Oh, right here. Yeah, this little header here. I was going to set this up to where I could actually, bit bang, set up a soft, serial port, because I need to use the regular serial port as a communications with the PC, because I want to be able to communicate with the PC too and send the data out. When I do data logging, send the data out to a PC so you can see it on a much bigger screen. But just for reference and to see what's going on quickly, you have this extra software serial port I figured I'd put in here somewhere, and these pins may change, and it would change in practice, but the point is that, if I could write a little drawing routine, since they have already got the GFX library or whatever on the little oscilloscope thing, I was like, well, if it's got any program memory left, yeah, I might be able to just send data from this RAM to that chip, or to that oscilloscope, and have it act as a display when I do that. So, because it does have a spare RS-232 port on it. And has a couple of other pins too, but not enough to where I think I could really drive memory and stuff like that. So I figured it's best to actually dump the data from the Arduino directly to this memory chip, instead of trying to send it over a slower bus under dubious circumstances. So if you want to do a display, it would just read from this SRAM and send it over a software serial port to the oscilloscope, and it doesn't matter, because that's not going to be live. It's just a data plotter. It's just you're just plotting the data log, so it doesn't matter how fast it is. It's not doing it live. It's just the data you've accumulated from doing a bunch of tests. You can, when you're ready, send it over to the display and have it display the graph. Like a tachometer, for example, you can actually monitor you know, determine, you know, what a motor's acceleration rate is. You know, instead of just measuring how many RPMs a motor goes, you can literally, with something like this, actually measure its acceleration curve. So you can see, you know, how it's kind of loading and all a bunch of other shit, you know, if you're trying to look at motors. So again, that's one of the other things you can do with this. In fact, there's a lot of things you can do with this, including measure temperature changes, like if you wanted to try to determine, you know, what the thermal resistance of a heat sink was. You know, you could take a couple of these types of probes and stick it on one side of the heat sink and the other on, you know, a heat source, and kind of measure the temperature differences as they rise, and you can get an idea of what the heat transfer rate, you know, as this temperature starts to increase, you know, versus the amount of power you're applying. You can probably calculate, you know, what the thermal resistance basically is of an unknown heat sink. So that's one of the things I was thinking about doing with this, and you may not need these types of probes for it, but what I like about these K-type thermocouples is that you can buy them that go up to, you know, well over 1,000 degrees centigrade, you know, about almost 2,000 degrees Fahrenheit. So, you know, by direct contact. So even the fairly routine ones can do 300 or 400 degrees. Again, they're a lot more heat tolerant than like a thermistor is. So, and since they're based on thermocouples, they're apparently more linear or predictable or what the fuck ever. Anyway, the point is that, you know, I had a couple of these modules I thought I'd use for things like that, and there's several other things I wanted to do with this circuit. Right down here you see like a bunch of different crystal oscillators I have, and you know, I would like this thing to run at least 20 megahertz. I'm afraid 25 might be too high, because I do have a 20 megahertz clock crystal on hand, you know, in a 14-pin size package, and I got a 16 megahertz crystal that's on one of those smaller half cans. But I got a whole kit of crystals in, you know, ranging from 1.8 megahertz clear up to like well over 20 megahertz. I know that. And again, I can't find an oscillator on the internet that will definitively work with 20 megahertz. So again, I got to actually try some of these circuits to find out which ones would work best if I wanted to actually do that. But I was like, well, it wouldn't hurt actually having a couple of different crystal oscillators, you know. But I didn't figure I would build all these, but just in case, I went ahead and designed it that way anyway. But that's what all that is. But it goes into this, you know, little device here, which is a 151. So it takes like any of these data lines and, you know, demultiplexes it down to, you know, one line as an output. So it's like a demux. Let's see. And this right here, this really just this thing here reads, you know, the actual settings, because how I did these channels right here, you know, this is a window comparator, and this is for your digital logic. This is a little thing that allows me to use a pull-up or a pull-down resistor in case I wanted to use, you know, like limit switches or whatnot. So that, you know, is an implementation of that. So it allows you to use it as a pull-up or a pull-down, or disable it since it can tri-state. Let's see, this right here is a one-shot multi-vibrator, so it's meant to be a switch debouncer for a single push button, you know, which drives a counter, which actually resets after it counts to 5, because we have 5 different configurations here that we can select from, you know, via this 151, which again is a, you know, demultiplexes it down to one line output, which is the output actual business end of the channel module. And you have a 138, which actually displays an LED, so you kind of know which mode setting it's in. But as a result, this is all done with digital logic. So the Arduino doesn't have anything to do with actually setting the controls. Again, I was trying to save pins on the Arduino, so I just decided to go ahead and do the whole thing with digital logic, you know. So this is, you know, one way of kind of doing that. So it'll cycle through each option and then reset, you know, so you just keep pushing the button until it's on the setting you want. But as a result, the Arduino doesn't know what the setting is, and there are times it would be nice if it just automatically did. So that's what this does. I tap off of this this count output from that timer, and it goes through this series of one of two selectors. So, and I've actually got them stacked, so it's actually, you know, you can take 4 data input lines and select between one of 3 sources. So, you know, this is the output. These data lines are all the input, so you can have up to 3 outputs. Because by default, these chips are one of 2, but you can stack them like this to make them one of 3 or one of 4 or whatever. But at any rate, I got that, and that goes into one of our shift registers, so the Arduino can figure out, again, it can strobe which of these 3 channels, 1, 2, and 3, that it wants to see what the settings are. It wouldn't have to do that often, so just maybe once a second or something like that usually. I mean, it's just for its own reference, so when it wants to run calculations, it'll know what to run calculations on exactly. Because again, I would have several different functions programmed into this thing, you know, for several different uses, you know, like a ballistic chronometer and, you know, a bunch of other you know, applications I had in mind for this specifically, as well as just general purpose stuff. But at any rate, that allows it to monitor that. And then 2, we have this window comparator with these potentiometers that actually set it, you know, set its voltage reference. And one of these can actually be set like all the way up, so where it's like 5 volts. But on our sensors, my sensor modules, I would limit kind of like this down here, so that it drops at least like 0.3 volts, and I maybe even use a regular diode there too. But so it would never, you know, none of my analog output sensors anyway would ever go above, you know, like 4.7 volts or less, depending on which diode I use. But that will keep it so that I can actually just like, you know, take one of these references and set it, you know, up above the input voltage level, so it effectively is not a window comparator anymore, but it's a single comparator. So I just use this lower one as just a regular comparator if I wanted to, you know, you know, I didn't want a window comparator for some reason. You know, it allows me to do that. You know, and again, some of this stuff is probably not necessary, but I always like to cover my ass. I'd rather have it and not need it than need it and not have it, if you know what I mean. Because it's not easy to add this after the fact, you know, if you went and built something like this. And this here, right here, is a simple zero crossing detector, which I haven't settled on the values yet, but, you know, the point is you could put some AC waves in there, and this reverse diode prevents it from going too low. But basically, this is powered by 5 volts, so on this side, you know, you're never going to see more than 5 volts, so, you know, that goes into a buffer, which you can, you know, disable or not, you know, which acts as a possible input too. So if you wanted to, you know, use this as a frequency counter, this is a good way to do it with a zero crossing detector. But you know, you can use one with op amps and stuff like that, but it's overly complicated, I think, and this is going to be a lot faster than most op amps would be. But what's good about it is that, you know, it doesn't matter. You can put like 50 volts in this thing, as long as you know, I don't know, I'd want to use this transistor to do that, because I think that's limited to like 30 or 40 volts, but you can put a higher voltage transistor here, and I might do that. Again, none of the stuff was set in stone. But the point is, you put an 80 volt transistor here, you know, I can put 80 volts into this thing, and that will not harm my circuit, because it's going through a transistor. That's all being, you know, going to ground. Oh shit, see, this is one of the things that pisses me off. You know, okay, KiCad, you know, is a you know, this is assembled directly from KiCad. You know, I didn't bother micking around with it, but you know, here we are. You know, they got the you know, the emitter is backwards. They got this, you know, shown as a PNP transistor when it's clearly NPN. So like I said, you know, I don't trust any of KiCad symbols. You know, you got to be careful about that. You know, it's just stupid shit like that you know, bugs the piss out of me. It's real professional people. But anyway, the fact of the matter is, yeah, you can use this, you know, as a zero crossing detector, and it's not going to heard if you wanted to measure something that's a higher voltage, you know, than normal, even if it's AC. Especially if it's AC, you're going to need it as AC. You know, of course, you could stick a capacitor here if you wanted to measure a fluctuating DC signal, because that would convert it to AC, and then you could. That it would be arbitrary. I don't know where the zero crossing point would be on it, but the point is that's what it's for, to be able to use, you know, so it can be used as a frequency counter. And some of this stuff may not be, you know, may still be a little half-baked. I just finished this thing, and I just, you know, to the extent I did, just so I can see if it would actually be plausible to use something with this little pin count to control this thing, like this Uno. You know, I was hoping I wouldn't have to use a Mega or something with more pins, so that's why I did a lot of this elaborate crap. Because again, I could have implemented a lot of this with a Mega, but then again, you'd have wires coming from a single source going all over the place, whereas a shift register, it's really just a few serial lines that makes it easier to route and to distribute your control, you know, as opposed to all the control lines having to come from a single point. And again, you know, I'm not going to go have a 4-layer circuit board or 6-layer circuit board made, and I'll be damned if I do that. Those aren't cheap. So, I mean, it's going to be a circuit board that I make or not at all. So anyway, but that's kind of the gist of what's going on with this thing. I think I've generally touched on most everything here, and this is just not only for if you're curious, but in case I 6 months later change my mind and decide I want to maybe go ahead and do this after all, I can watch this video and pick up and see what my thinking was. Again, I got notebooks full of information too, but that does get confusing when you try to come back and try to read your own writing after, you know, 6 or 8 months. So that's why I'm doing this, not just to bore people, but, you know, just in case I change my mind. So anyway, that's what's going on with this, but that's also why this is pretty fucking elaborate. So I'm just really not, you know, inclined to, you know, want to do a bunch of stuff like this, because again, I can do most of this stuff out of the Arduino. It'll just be slower. So I think that would be the best way to do this. So anyway, that'll conclude this video.